And I'll show my, just shut, oh, continue. Cool, so you guys should be looking at my desktop now. I'm going to be showing RefNX today, which originally started development, I guess, in about 2011 in its early stages, but some parts of the code base go back to about 2005. And the idea for the rationale for this is that it's a modern open source replacement for MotoFit, so for analyzing neutron X-ray data, and we've got some bits coming in now for ellipsometry. It can do pretty much, well, it can do everything that MotoFit can do, so co-refinement of multiple contrast data sets, but a whole lot more. And 20 minutes or 15 minutes isn't really going to do a huge amount of justice, but we'll see how we get to. So it's hosted on GitHub at the RefNX, on the RefNX organization. It's written in Python, which lowers barrier to new contributions and issues and documentation, and new code is always welcome to help improve the code base. It's well tested, so it gets continuous integration via GitHub Actions, where you can check that if you make changes to the code, then the changes that you made, they're correct. You can install RefNX from PyPI, so it's pip installable. You can also install it from CondaForge. But there are also standalone executables, which I'm going to show you today. This is the standalone GUI, and I'm going to show fitting in this. But and you can get these standalone GUIs either by pip installing the RefNX package and then typing RefNX at the command line, or you can go to the releases page, and there's a standalone app. There's a standalone app for Mac and a standalone exe for Windows, but it will also run the GUI on Linux, but I don't have anything to package that on, at least I'm not even sure you can package into single executables on Linux. So RefNX is fast and performant and extensible. You can run it on anything from your own PC up to using clusters for high performance computing for Markov chain Monte Carlo analysis. Yeah, so the code is on GitHub. There's a read the docs online where you can go for tips on how to install the package with Conda or pip, getting started, so how you go about starting to fit a model. And this would be fitting a straight line, in fact, so it can fit non-reflectometry data as well. Describes the GUI, how to use inequality constraints, equality constraints, and so on. A little bit of a demo on model selection, and so on. So that's a good port of call for first help. I also have a YouTube channel where you can go and watch videos on how to do various things. So I'm always up for doing new YouTube demonstrations if they're required. So RefNX is, Stuart and I wrote a paper on RefNX got accepted in 2019. It's an open paper from Journal of Applied Crystallography. And the general idea is, the general setup of the package is that you have a whole series of parameters, and the parameter may have a value associated with it, whether you're going to fit it or not. So, and then some bounds, and the bounds can be anything from a uniform distribution through to any statistical distribution from scipy.stats. And then you basically define your interface by a series of components. The simplest component is a slab, which has uniform SLD over its thickness. And so the slab has various parameters associated with it. So thickness, scattering and density, both the real and the imaginary parts you can fit, the volume fraction of solvent, and a roughness. The roughness is typically Gaussian, but you can also do linear steps, sine. I think there's a whole range of different roughness models. And as well as fit, so this SLD part is you're fitting a scattering length dense, you create a scattering length density by a complex number, I guess, but you can also create a scatterer by providing a molecular formula, chemical formula, and a mass density that you then fit. So the slab is the simplest component. We have different components such as lipid leaflet or splines or components for polymer brushes and so on that enable you to describe a subsection of the interface and parameterize it into something that's chemically relevant. So you chain a whole series of components together to make a structure. The structure goes into a reflect model, and this model then applies resolution smearing and adds a background. So it makes it into an instrumental thing. The model is then combined with a data set to make an objective, and you can calculate various stats on the objective like log prior, log likelihood, chi-squared, and so on. And then you can then finally combine lots of objectives together into a global objective to enable co-refinement of multiple data sets, multiple contrast data sets, or X-rays or neutrons or what have you. So that reduces the parameterization in your system or improves you can reduce the parameterization by sharing parameters across the model. So you can reuse a parameter to set up, say, like the thickness parameter, and share the same parameter across multiple models. That's what I was trying to say. So that objective gets put into, can go into global objective. The objective can also go directly into a curve fit, which then does least squares fitting. You can do Markov chain Monte Carlo of the posterior. And so there's various solvers that it can use. So like Levenberg-Marquardt, LBFGSB, so various solvers from SciPy, differential evolution. And it also has access to various Bayesian analysis sampling techniques to work out the posterior distributions for all the parameters. And so the various ones it can access at the moment, or that are inbuilt, are MC, PTMC, which is a parallel tempered Markov chain Monte Carlo, and both those are used a lot for astronomy. PyMC3, which is one of the default ones for Python, and also Dynasty. And Dynasty is a nested sampling package, which you can use for model selection. And these are the kinds of things that you get out of the Markov chain Monte Carlo. You can basically characterize the parameter probability distributions that are consistent with the data. So here, this correlation matrix here in this corner plot would show a inverse correlation with that parameter and this parameter. So that's the paper on the project or on the package. And all the data sets in the package were done in a Jupyter notebook. So RefNX was designed to be aid reproducible research, and Jupyter notebooks, for those of you who are unaware, allow you to mix text, but also they have different cells, and in one cell you might have text, but in the next cell you could have an executable piece of code. And the idea behind this is that you can write a notebook and then attach it to your supplementary information, and then submit that with your paper. And then people who read the paper can then go off and reproduce the data analysis that you did for that paper. And so what I'm showing you in this, window here is analysis that we did for the RefNX paper on a lipid system. So here's where we're making a a structure composed of silicon dioxide, 2 leaflets of a lipid bilayer, and then followed by the solvent. And you see here, we're reusing the solve roughness parameter. So instead of 3 different parameters, we're decreasing the number of free parameters. And then the inner leaflet and outer leaflet are also shared across all these different contrasts, or across these different structures, and they're solvated by this final solvent. So the Jupyter Notebook is designed to enhance reproducibility. You can actually download that from the RefNX paper on Journal of Applied Crystallography. But I'm not going to show you how to set up a model in a Jupyter Notebook because it's pretty difficult in 10 or 15 minutes. So I'm going to punt that to homework, where you guys, if you're interested, can go and open that up and see if you can reproduce it. One advantage of the Jupyter Notebook is that you can also run them in binder instances, and this is an online reflectivity, an online resource for running Jupyter Notebooks. And actually the analysis repository that belongs to also is binder capable, and then in the tutorials directory we can actually also run notebooks that a few of us have developed that will also do run the GUI-based analysis that I'll show you today in RefNX, but we'll do it in a Jupyter Notebook. So you can basically repeat the same analysis in a notebook rather than the GUI. So what I'm going to do now is show you how to fit in the GUI. And it's a good starting point for a lot of analyses because it's fairly capable. I'm just going to unclick that to give myself a bit more working space. So in the graph, you've got reflectivity as a function of Q. You can do it fit as ln R versus Q, log R versus Q, RQ to the 4 versus Q, or RQ squared versus Q. In the command line context, you can basically give it any transform you want if you don't like those. So like fitting of R over RF or something along those lines. So we've got the reflectivity graph, then the SLD profile. So let's load a data set. I grab the data set, here's one I made earlier, just drop it onto the graph and it populates the graph. Or you can load it from the menu, data load data. You can also refresh data. So if you've got a piece of data that's coming off the beamline, you can just press Apple R or Control R and it will update. I'm going to just collapse that model and go back to the one that we're going to fit. So this is the data set that we want to fit. I'm going to drag it over to here. And these are the list of data sets we're going to be fitting. So that here in the structure, it's going to be our fronting material is going to be silicon dioxide. So I'm going to change that from 0 to 2.07. I'm going to change the backing SLD to 6.36. This first layer here, well, this is going to be silicon dioxide, so I'm going to change its name to make it a little bit more obvious. Now, we want to add in another layer here, so press the plus sign. This particular sample is silicon dioxide, polymer, and then solvent. So I'm going to insert a layer. It says, what component would you like to add? So the built-in components that are available in the GUI are a simple slab, a lipid leaflet. So lipid leaflet is useful for fitting lipids or like absorbed surfactant monolayers, for example. A spline, which uses a freeform method to basically freeform model a section of the interface, or a stack, and that's useful for multi-layers. I'm just going to add a slab. I'll start off by adding trying to add a leaflet. So it comes up with this dialog first, and you can basically add a whole series of we've got, populated it with a whole series of lipids that my colleague Anton Lebrun has calculated the SLDs for and has got head group volumes and so on from various papers. We're not actually going to add a leaflet, we're going to add a slab. So I'm going to add a slab in again. This is going to be our polymer layer. The polymer layer is about 200 angstroms. This SLD, well, we'll start off at 2. Let's say that the background is going to be 2 × 10⁻⁶. There's a slider at the bottom which allows you to fiddle with the thickness if you want to. You then select the parameters you want to fit. We'll fit all these. You can fit the resolution if you wanted to. By default, it uses constant delta Q on Q, but you can also, it also ingests the resolution from the data set as well. And this particular instance, I want to fit this the polymer roughness. And this roughness here is the roughness between the polymer layer and the silicon dioxide. And I want to make a constraint so that it's equal to the backing rough. And the backing rough is between the D2O and the polymer. I want to make those two equivalent. So in order to do that, I select the parameters, right click on link parameters. And you see here that you can link equivalent parameters on other data sets. So if we'd loaded in multiple contrast data sets here, so we had 2 or 3 or 4 or 5, whatever, contrasts on the same model, it would, if we clicked link equivalent parameters on other data sets, it would link, if it's exactly the same model, it would link all those parameters that you'd selected, which is an easier way of setting up the model. In this context,
just so you know, Andrew, there's about 2 minutes left.
Yeah, okay. So link parameters, and you see here that this one has been linked in the constraint column. And if I change that to say 4 or 5, then that would want to also fit the silicon dioxide thickness. 4 or 5, so that when I change that roughness parameter, it updates here as well. Once you're happy, you set up the limits. So this is a quick default way of setting up the limits. You then click go. And the default fitting algorithm is differential evolution from SciPy. And there you go, there you have your fit, you have the SLD profile. There's the parameter uncertainties in this, the estimated parameter uncertainties in this column. You can also, with the GUI, use the various different algorithms, including Markov chain Monte Carlo with MC. And the output from MC is down here. So you get out, you can get out the correlation matrix. This is one I prepared earlier. You can see the correlation here. You also get out all the chains and the parameter values as you do a different number of steps. There you go, I'll stop there. So a quick rundown on the GUI, a little bit of a rundown on the Jupyter Notebook, and I'll take questions there.